Okay, so for this lesson, we're going to be looking at combinations. So before we get started, let's start with a quick little example just to recap some of the past topics we've covered. So this is a question we've done before. In how many ways can 5 students be arranged in the positions of president and vice president of student council? So what I'm going to do is I will outline my 2 spots for president and vice president. Now we have 5 students, so that means we would have 5 choices for president. Then because 1 student has already been selected, we have 4 students for vice president. Because we require a president and a vice president, we multiply, which will give us 20. Now, the other way we could have done this is we could have used a permutation, right? Because the order matters here, and having student A as president and student B as vice president is different than having student B as president and student A as vice president. So for my permutation, I have 5 students, and we're giving roles to 2 of them. So 5 permute 2 is going to give us 20. So either way you do it, you should end up with 20. Just like that. Okay, so these are permutation questions, which we have done before, where order really matters. And we've mentioned that a few times, that the order in which these things are chosen matters. Again, it's a different arrangement if student A is president and student B is vice president than if student B were president and student A were vice president. Those are 2 totally different scenarios, so that's why order matters. So now let's switch up the question a little bit. Now let's consider the same 5 students, but this time they're running for 2 co-president positions. In this case, order doesn't matter. It doesn't matter if I have student A and student B as co-presidents, or if I have student B and student A as co-presidents. Those are the same thing, right? The order in which they're chosen does not matter. They are just both co-presidents. So we want to try this and see if we can determine how many ways that this can happen. And we want to think to ourselves first, do we think there will be more, the same, or fewer ways that this could happen? So it's kind of like our identical elements a little bit, right? Now having student A and student B is the exact same situation as having student B and student A, just like an identical element. So that's exactly what we'll write. There should be less, and that's because student A and student B is the same as student B, student A. Those 2 scenarios are identical now, so it's kind of like our identical elements where we will be getting rid of some of our options. So what we would do here is would have our number of ways. Because we have 5 students, we would take 5 factorial. And then what we would do is we would make sure to divide out our number of identical terms, right? Just like this. So we will be getting less options. That's what's happening here. Are there any? Oh, and I forgot one other thing. Those are for the 2 co-presidents, and those are for the other people who are not chosen. Because those people who are not chosen, they're also identical elements too. Sorry, my bad. I forgot that right away. Okay, so This is slightly different, this situation. If I look here, this 5 factorial divided by 3 factorial, this here is 5 permute 2. That's the same thing as what we were doing before. That's what that is. So if you put that into your calculator, we will get the same answer as above. This is the part that's new, this 2 factorial. And this part is here because what we're doing is student A and student B is the same thing as student B and student A now. In this case, if I put this in my calculator, it equals 10. So we do have less options. Now, in this case, because order doesn't matter, this is called a combination and not a permutation anymore. And we can write this out in 2 ways. We could say 5 choose 2 and write it like this, or we can write it like this, 5 choose 2. You will see both of these written out, so it's up to you. But how we say them is 5 choose 2. That's what that means. We're using a combination because order does not matter here. We'll go through and do a ton of examples too to help you understand a bit better. Are there any questions so far? Okay. Okay. So this whole thing, this is a good question. The question was, after I did 5 choose 2, do I still have to divide it by the 3 factorial? Nope, because this entire formula here is the formula for 5 choose 2. And that is the next piece that we'll be talking about. So no need to divide anything else. That whole thing takes all of the math into account. And it gives us this lovely formula. So n choose r is equal to n permute r divided by r factorial. That's what's happening. Now, if I go through and I simplify it, we get this lovely formula right here, n factorial all over n minus r factorial multiplied by r factorial. Now, what does this represent? What does it mean? It represents that if, for example, we have 10 choose 3, it represents that if 10 items are arranged in sets of 3 where order doesn't matter. That's what that means. So it means out of my 10 things, I'm choosing 3 things, and the order in which I choose them isn't important. Now, again, you will see this notation or this notation. I'll try to use them interchangeably because if you are looking at additional resources or you use this stuff in the future, you will see both. So I'll try my best to use both of them just so we're used to seeing both of them. Okay, let's do some examples because that's the best way to understand this stuff. So the first example says Frank, Jerry, Harold, Isaac, and James competed in a race. In how many ways could these men be awarded the gold, silver, and bronze medal? The first thing we do with any question is we think to ourselves, does order matter? If we have Frank winning gold, Jerry winning silver, and Harold winning bronze, is that a different situation than Isaac winning gold, James winning silver, and Jerry getting bronze? Yes or no? Are those different situations? Because they are, that means order matters here. So our order matters, which means this is a permutation. Right? Because the order in which they finish the race matters, that's a permutation. So we solve it just like we were doing before this lesson. So we have our gold, bronze, and silver. So we have 5 people total. So 5 people could win the gold. Then after that is handed out, there are 4 options for bronze. After that is handed out, there are 3 options for silver. Because we're giving out a gold medal and a bronze and a silver, we multiply. Oops. And that will give us 60 options. So we can do it that way using our fundamental counting principles. Or we could have done it this way, 5 permute 3, and used our permutation formula, which is 5 factorial all over 5 minus 3 factorial, which will still give us 60. So it doesn't matter how you do it. You could use the permutation button, or you could use our fundamental principle. Doesn't matter. Okay. So that's very similar to what we had done before. Now for part B, a party is held for the 3 medalists. How many different groups might attend? So the first thing we want to think about is, does order matter? So if we have Frank, Jerry, and Harold being the top 3, they get to go to the party. If we had Harold, Jerry, and Frank winning, they're still the top 3 finalists and still gets to go to the party. It doesn't matter who is first, who is second, who is third. We're just choosing 3 of them to go to the party. So order does not matter here. And therefore, this is a combination. Again, how do we know that? If we have Frank first, Jerry got bronze, Harold got silver, all 3 of them get to go to the party. That's the same thing if Jerry got gold, Harold got silver, and Frank got bronze. That group of 3 still goes to the party. It doesn't matter what order they were selected in, they all still get to go to the party. Okay. So for the next piece here, we'll solve the combination. So here we have 5 people and we're choosing 3 of them to go to the party. I realized I accidentally made a mistake in my solutions and it says 5 choose 2. Just a heads up, it should say 5 choose 3. So we have 5 people. We're choosing 3 medalists to go to the party. So we have 5 factorial all over 5 minus 3 factorial times 3 factorial. So that will give us 5 factorial all over 2 factorial, 3 factorial. Which is 10. And also make sure that you're comfortable finding your combinations button on your calculator. It should look something like this. Some say N choose R. Some maybe use different variables. Same deal. Okay. So part C says, how are the results of the number of ways the medals can be awarded related to how many different groups could attend the party? So there's a couple wording pieces that we need to talk about. So part A, that's the number of arrangements. That's what that means, number of arrangements. When we're using the word arrangements, order does matter here, right? That word arrangements is talking about the order in which everybody is chosen. So the order really matters. This is talking about who's first, second, third, how are those people arranged. For part B, here, what's going on is B is A, but we've basically gotten rid of any doubles. And that's because order doesn't matter. So what we're doing is, because the order doesn't matter, it doesn't matter who got first, second, and third. Jerry, Frank, and Harold can all still attend the party. And maybe Jerry got first, Frank got second, Harold got third. They still attend the party as a group of the three of them. Any questions about that before we do our next example? There can be a bit of a steep learning curve with these. Okay. So we'll keep doing some examples, because the more examples we do, the easier this becomes. So for 4, it says, how many ways can a coach choose a starting lineup of 5 basketball players from a team of 12? So because we're just choosing the group of players, we're not assigning them roles, we're just choosing them all. That means order does not matter. So we're just choosing a starting lineup. So order does not matter. That means it's a combination. Right? If we were assigning specific roles, then that would be a permutation. But because we're not, we're just picking 5 people, that's a combination. So there are 12 people. The coach wants to choose 5 of them. So we do 12 choose 5. So we'll have 12 factorial all over 12 minus 5 factorial multiplied by 5 factorial. Quickly do that on my calculator. I'm going to do it the long way. And we should get 792. Go. So make sure that you are getting the same thing when you also use your choose button with the C there. But the trickiest part of these is to know when order matters and when order doesn't. Okay, any questions so far before we move on to a couple of different examples? Okay. So there are a few special cases, and some of these we've actually done similar questions to already, just with organized counting. So the first is what's called a combination of binary choice. And for combinations of binary choice, these are for yes/no decisions. This is kind of like the window question from, I think, the first homework. This is where I look at a bunch of different items and I say yes or no, yes or no, yes or no, yes or no. Just like the windows. Is it open or closed, open or closed, open or closed? Now, you'll notice that we have 2 formulas to this. It's either 2 to the n or 2 to the n minus 1. This means if we're excluding a 0 option, that would be the case in which I say no, 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 no to all of them. And there's only one way to do that. So if you can't have a 0 option where you choose nothing, then u minus 1. That's just the idea. So let's do an example to show you what I mean. So Hannah attends a potluck lunch and can choose from macaroni salad, potato salad, green salad, hamburger, sausage, and or a cookie. Assuming a maximum of 1 serving of each possible dish, how many different lunch combinations are possible for her to eat? So the first thing, we need to assume, can she take no food? Are we going to include the 0 option? We'll assume that taking no food is an option. Assume taking no food is an option. That's the important piece there. So we're going to include the situation in which she could say no to everything. So you can use the formula, but I'll show you how the formula works and why we use it. So I'm going to look at all the foods individually. So we have macaroni salad, potato salad, green salad, hamburger, sausage, cookie. Is that everything? 1, 2, 3, 4, 5, 6. Macaroni salad, potato salad, green salad, hamburger, sausage, and cookie. So what we're going to do is we want to think of how many options there are for each of these. So for macaroni salad, is she going to put that on her plate? Yes or no? 2 options. Pasta salad, is it going on the plate? Yes or no? 2 options. Green salad, going on the plate? Yes or no? 2 options. Same with our hamburger, 2 options. Same with our sausage, and same with our cookie. Because she had to make a decision for the macaroni and the potato and the garden salad and the hamburger and the sausage and the cookie, we multiply, and this will give us 2 to the power of 6, which is 64. So that is where the formula comes from. The only thing that could be different is if she had to pick at least one thing, in which case we would subtract 1 because picking 0 items is not an option. Actually, we can include that one in too. So that's if we're assuming taking no food is an option. Let's just add in the other option so you can see both. If we assume she must take at least 1 item, then same idea. We would have 2 to the 6, but we have to subtract the situation in which she takes nothing. -1, so that would be 63. In a question on an assessment, I would be very clear as to whether or not you include that 0 option. Okay. Any questions before we do our last example? Okay. So for this one, we're going to look at combinations of items of which some are alike. So the total number of selections that can be made from P items of one kind, Q items of another kind, R items of a third kind, etc., is going to be P plus 1, Q plus 1, R plus 1, and we only subtract 1 if necessary. Same idea as above. We subtract 1 if I'm allowed to, we subtract 1 if I have to pick at least one thing, right? I can't choose none of them. Now, the reason why we add 1 here, if you're curious where this is coming from, is because we also want to include the 0 option. So we want to include being able to pick 0 of something, 1 of it, 2 of it, 3 of it, 4 of it, because we also want to include the opportunity to pick none of them. That's why we add the 1. Okay, so this one here says that a bag of marbles contains 4 blue marbles, 6 red marbles, 5 white marbles, and 3 green marbles. How many ways can you reach into the bag and draw some marbles if you must draw at least 1? So we must draw at least 1, which means we cannot have a 0 option, right? So we will have to subtract 1 at the end. If I did have an option where I didn't have to pick 1, I wouldn't have to worry about that. Okay, so what we'll do is we're going to do this 2 ways just so you can see where the formula comes from. So here's our options for the blue marbles. I could choose 0, 1, 2, 3, 4. So 5 options. For the red marbles, I could select 0, 1, 2, 3, 4, 5, 6. 7 options because I included that 0 option too. For the white marbles, I could choose 0, 1, 2, 3, 4, 5. So 6 options. And for the green, I could choose 0, 1, 2, 3. Now, because I require a blue marble, I need a choice for the blue marble and the red and the white and the green. I multiply, and then I need to subtract 1 because I have to pick at least 1 marble. So that will give me 5 times 7 times 6 times 3 minus 1 is 629. 5 times 7 times 6 times 3. Oh, 629. I'm going to re-upload this solution because there's a couple of errors on the one I posted. So I'll re-upload this one because there's a few errors here. So that's one way to do it. The other way that you could do it too is you could use the formula. So for the first one, we have 4 blue marbles, 6 red marbles, 5 white marbles. Oh, here's my mistake. Never mind. That should have been a 4. There we go. Sorry about that. It was 839. Here we go. But I could have also done it like this and written it out this way. It doesn't matter how you want to do it. Whatever you're most comfortable with is totally fine. Okay. Are there any questions about that at all? That was our last example.